We are now ready to address the general problem of what is known as sequential probabilistic inference, or state estimation. And that's what we do in this section, and then we kind of go over and talk about it a little bit more in the next section and break it up into kind of small baby steps, and then after that we use it to derive the Kalman filter and other filters that follow. The notation that we use is described here. If you have a variable with a superscript minus sign, that indicates that the variable that we're talking about is a predicted quantity. The prediction is based only on past measurements, not on a present measurement. So the minus is used to give you the idea of some kind of a deficiency. There's a deficiency of data available. I can't estimate, as we'll see, the value right now because I don't have measurement right now, but I can predict what that might be based on past measurements. A superscript plus, on the other hand, indicates an estimated quantity. So there's a difference between a prediction and an estimate, and I'll try to be careful and precise when I use the terms. An estimated quantity is also some guess as to the value, but it's based both on past and present measurements. So there's no deficiency in the data set. It uses all available data. When I have the decoration hat, so this might be an x minus, this might be an x plus for a predicted state and an estimated state, whenever I have either a predicted or an estimated quantity, we use the hat on top to show that this is not the exact value, this is some guess to the value of x. If I have a decoration that's a tilde, so x with a tilde on top, that's the difference between the truth and the predicted or the estimated quantity. So x tilde minus equals x minus x hat minus, and x tilde plus equals x minus x hat plus. The symbol sigma is used to denote a correlation, just as we've seen in the previous sections, between the two arguments in its subscript. And it's an autocorrelation if only one argument is given. So sigma xy is the expected value of x times y transpose, just by definition. And sigma x is equal to the expected value of x times x transpose. And when the arguments are zero mean, as they often are in the quantities we're working with, then the correlation is the same thing as the covariance. So we write something like sigma sub x tilde y tilde. We recognize that by the definition of our sigma notation must be the expected value of argument 1 times argument 2 transpose. But argument 1 is equal to, so x tilde equals x minus x hat. Yes, it is. And the expected value of x tilde, if it's a zero mean quantity, is going to be 0. So if this is 0 and this is 0, then these two lines are the same, which means that the correlation and the covariance are the same. So that's why I can use the same symbol, just with different arguments in the subscript to denote either a correlation or a covariance. That is the notation, and there's usually a subscript also to indicate the time step, so a subscript k, for example. With the notation defined, we have to define what the problem is we are trying to solve. And the sequential probabilistic inference problem we're trying to solve is this. It's on the right-hand side. It says, I want to find the argmin of the expected value of xk minus x hat k plus, the norm squared of that vector, given yk. It's like, well, if you're really good at math, you can parse that, but let's do it a piece at a time. X hat k plus should be a plus in here. So x hat k plus is an input to this, and that's what I'm allowed to change. Everything else inside of this function is fixed. Yk is the sequence of measurements. That's completely fixed. I've measured them. Before I measured them, they weren't. They were random, but now I've measured them, and so I have that data. Xk is the true state, which I don't know. I can't measure it, but I can use it in math as long as I don't use it in an algorithm. So I'm trying to find, this argmin says, return the value of x hat k plus that minimizes everything in the round brackets. So I'm trying to find the value of x hat k plus that minimizes everything in there. Well, what's in there? I've got an x minus x hat k plus. So this is a distance. This is the difference between the true state and the state estimate. And I want to minimize that difference in some sense. And there's lots of different cost functions that I could come up with to minimize. This one is called the minimum mean squared error. So it says first I'm going to square the error. It takes this x minus x hat plus. The 2 norm is so some vector v 2 norm squared is equal to v times v transfer. Sorry, it's the other way around. It's v transfer times v. And so it's the sum of the squares of all of the elements of that error vector is what we're actually summing up. And we use it because it makes the math easy. But if any one of the components of the error vector is large, then v transpose v will be large. And I'm trying to minimize v transpose v, so that's going to tend to try to minimize all of the errors. Because I'm squaring everything, the sign doesn't matter. It's saying a negative error is just as bad as a positive error, and so forth. So I'm taking the error, I'm squaring it basically, and I'm finding the expected value of that error given all of the measurements, and I'm trying to minimize that expected value of the error given all of the measurements. So I take the error, I square it, I find the mean or the expected value, and I want to minimize that. So minimum mean squared error. Writing that out, the 2 norms squared I can write out as x minus x hat plus transpose times x minus x hat plus. And then I can use standard algebra to be able to work with that a little bit. So I use FOIL. So x transpose times x is x transpose x. And then I have a minus x hat transpose times x. And I also have a minus, well, I have an x times a minus x hat transpose. Those turn out to be the same thing. If I have what I have here, I've got a vector times so this is v1 times v1 transpose times v2. That's equal to v2 times v1 transpose, because the result of both of these is a scalar. It's a one-by-one thing, and the transpose of a scalar is itself. So I can write it either way, and so when I take both of them, I switch how I write one of them and combine the two together to get that term there. And then finally, it's minus x hat transpose times negative x hat, which is positive x hat transpose x hat. That's what I'm trying to minimize. Now, when we minimize a function, one way of doing it, at least analytically, is to take the function and set its derivative to 0 and solve. And even though this is a vector equation, it turns out we can still do that if we invoke some vector calculus relationships to help us. So what I want to do, I solve for x hat plus by differentiating this cost function and setting the result to 0. So 0 equals the derivative with respect to x hat of expected value of x transpose x minus 2 x transpose x hat plus x hat transpose x hat given yk. Now you may never have seen vector calculus identities before, so I list these here for your reference. Not going to prove them. They are in a number of textbooks and appendices to textbooks and so forth. But it turns out that if I have a generic y transpose x and I'm taking the derivative with respect to x, the derivative is y and the others that we have listed here. So let's go term by term. The expected value operator is a linear operator, which among other things means that I can pull the derivative inside, which is exactly what I do. So I take the derivative of x transpose x with respect to x hat, and I find that that derivative is 0 because there's no x hat in it at all. It's just a constant. A derivative of a constant is 0. Then I look at something which is minus 2 x transpose x hat. Well, that looks like this, where y is minus 2x minus 2x, and in this operation, so the output then would be minus 2x. So I've got this minus 2x is the output of that derivative operation. And then I have an x hat times x hat, which looks like this if the identity matrix, if A is the identity matrix. So over here on this side I've got identity plus identity transpose, which is 2 identity times x, or just 2x. And so I've got minus 2x hat. It all works out. Spend a few minutes looking at that, and this is what I get. So vector calculus, fantastic stuff. It allowed me to get this to be my result. Now I evaluate it. The expected value operator again is linear, which means, among other things, that expected value of A plus B is expected value of A plus expected value of B. So the expected value of minus 2x given y is minus 2 times the expected value of x given y. And then distributing the minus in, the expected value of plus 2x hat given y is in fact equal to plus 2x hat because x hat is the result of this. It's not a random variable. It's basically a constant in terms of the operations that we're doing. And so the expected value of a constant is itself, so it just comes outside of this operation. So I have all of this equals 0. Divide both sides by 2, and I get x hat plus equals the expected value of xk given yk. So we pause for a second. We're doing the general probabilistic inference solution. We defined a cost function which hopefully made some sense. We're minimizing some squared error. And the answer to that is that the best guess, the best estimate of the state to solve that cost function is the expected value of the true state given the sequence of measurements that I have taken up until this point in time. So I've got some huge multidimensional probability density function on x given y, because y is some huge multidimensional thing. But I just find the balance point in that density function, and that's my best guess as to what the state actually is. And that gives us some insight into the term expectation also. This is what we expect x to be. Now it could be, it's a random thing. It's with 0 probability going to be exactly equal to that, but it's going to be close to that, so that's what we expect. Now, this is an equation, but I can't implement this equation. I can't make a sequence of computer steps that says, okay, let's implement this. So our objective now is to find a way of computing expected value of x given y that is efficient and all of that. And we're going to assume something that we don't have time to show necessarily why we assume this. Again, we do that in the common filter course, but it would take too long here. We're going to assume that the random variables have a Gaussian distribution. We've said that before, but we're also going to assume that the result has a prediction correction mechanism. We don't know why we would assume that or look for that, but in fact, it does. So with malice aforethought, in other words, I've done this before, so I know that it's going to work. I'm going to define a prediction error, x tilde k minus, the minus tells you it's a prediction and the tilde tells you it's an error, so that equals xk minus x hat k, and x hat k minus, so this is x hat k plus, that's an estimate, this is x hat k minus is a prediction. Notice the only difference is what I'm conditioning on. The estimate uses all available data, the prediction uses all past data. Again, error is always truth minus prediction or truth minus estimate. We can't compute the error in practice because we don't know the truth. If we did know the truth, we wouldn't need a common filter, we'd just use the truth. But we can prove statistical results and come up with an algorithm, and that's what our objective is here. We're going to define also something called an innovation, which is y tilde k, which is y minus y hat k. And that is what is new in the measurement, because y hat k we define to be what we expect the measurement to be, the expected voltage, given all past measurements of voltage. So this is before I actually make the voltage measurement. I predict, if you will, what the voltage measurement will be. And then I measure the voltage, and the difference says, oh, I'm surprised. It's not exactly what I predicted. So my surprise factor is what is the new data in the measurement. That's the innovation. X tilde minus and y tilde can be shown to be zero mean random variables. We use the method of iterated expectation, which I don't derive here, but it turns out that the expected value of x given y is equal to the expected value of x. So I iterate twice to get the expected value of x back. So, for example, the expected value of x tilde minus is equal to, by the definition of x tilde minus, which is x minus x hat, so it's the expected value of x minus x hat, but the expected x hat is itself this expected value of x given y. This, by iterated expectation, expected value of x given y is just expected value of x. So this whole thing is expected value of x, and I get expected value of x minus expected value of x equals 0. Same thing for y. So if I use these definitions for my prediction of the state and my innovation, and similarly the estimate of the state, all of these quantities are going to be zero mean quantities. We can also show that the expected value of x tilde minus given previous measurements is uncorrelated with the past measurements because they've already been incorporated into x hat. So we can show that the expected value of x tilde minus given past measurements is just the expected value of x tilde minus without the past measurements. They've already been built in. And we do that by saying x tilde minus is x minus expected value of x given y, all of that given y. And we can iterate those expectations and come out with those two things being the same, because conditioning twice on y doesn't help. So I condition this one on y, I condition this one twice on y, but they still end up being the same thing. They end up being 0, and so they end up being this as well. So on one hand, we can rearrange the expression and we can write that the expected value of x tilde minus given all measurements up to and including time k is the expected value of xk given yk minus the expected value of x minus given yk. We can write that. On the other hand, we can write the expected value of x tilde given y is the same as the expected value of x tilde given past data and the present data, and conditioning on the past data we found out wasn't helpful, so this is irrelevant, and that gives us this result here. And we can combine these two results together. These two things are the same, so that must equal that. Plugging everything together and solving, we have x hat plus x hat minus equals this conditional expectation, rearranging, and I get this x hat plus equals x hat minus plus the expected value of x hat minus given yk. So this is what we call a prediction correction sequence of steps. Inside of our sequential probabilistic inference, we're going to do step 1, which is find x hat minus k equals expected value of xk given past data. And then in step 2, we'll say x hat plus k equals x hat minus k plus this new expectation of x tilde k minus given yk. We will repeatedly execute step 1, step 2, every iteration. I predict the state and then I correct the state based on a measurement. Predict, correct all the time. We'll see in more detail how this applies. This is still very conceptual in this section, and we'll see how it applies as we go forward, and we'll end up with actual algebra steps. But there is something here that we really haven't even gotten past the conceptual stage with, is what is the expected value of the prediction error given the measurement. And there's a derivation involved to show this. It's actually fairly involved, and it's in the Kalman filter course if you want to go and look it up. I'm not going to prove that here, but the expected value of x given y turns out, for just generically jointly distributed Gaussian variables, to be the expected value of x plus the cross correlation, the cross covariance between x and y, and the inverse of the autocovariance of y, all multiplying y minus expected value of y. Probably not something that we could just think of off the top of our heads. Like I said, the derivation is fairly involved and more lengthy than I want to get into here, but we'll use this result. And applying it to our problem, we replace the generic x with x tilde minus the generic y with y to get what we want to find. Expected value of x tilde k minus given yk is equal to the expected value of x tilde k minus plus this cross covariance between these two things, which we use a minus sign because we're talking about x minus, and then the inverse autocovariance, and then y minus expected value of y right there. We expand this out just a little bit by saying y tilde equals y minus y hat, which means that y equals y tilde plus y hat. So I replace y with y plus y hat, and expected value of y as expected value of y tilde plus y hat. We know that the expected value of x tilde is 0, so that comes there. We know the expected value of y tilde is 0, so that is there. The expected value of a constant is a constant, so the expected value of y hat is simply y hat. And these I just copy down, and we see that y hat is canceled out. I've got a plus and a minus, so those cancel out, so I simply get a y tilde. This bunch of correlation covariances really is just given a name, L sub k, and when I do that, I get this general update equation for the update step. So there's a prediction step and a correction step. And the correction step says take the prediction of the state, take the innovation, which is the surprise, that's the difference between the measurement and what I thought the measurement was going to be, and multiply by L. And this L is a blending factor between what I thought the state would be and something that the measurement, some new information the measurement is telling me to get the estimate of what the state is. And we're going to unwrap this more. This is only the first time we're seeing this, but especially when we look at the Kalman filter, we'll spend a lot of time looking at the structure for LK that we've derived now, but there's no intuition to be seen there yet. There will be intuition, but at the moment, let's just accept the math as is. One thing we notice, though, is that there's these covariances of variables that are required to implement this, and because of that, we not only have to compute an estimate of the state, it turns out we have to compute a covariance of that estimate and keep that in the Kalman filter. We need to compute these error bounds, if you will. L is going to be a function of the autocovariance of the estimate, and the autocovariance of the estimate is this. It's the expected value of x minus x hat transpose, and we know that this relationship is true. The x hat is equal to x hat minus plus ly. So the x hat I replace by x hat minus and then ly, and I do the same thing over here. And I put parentheses around this term because that's simply x tilde minus, and that's x tilde minus. And that allows me to write this as x tilde minus L times y tilde. And then we expand things out using FOIL. So expected value of x minus times x minus is sigma x minus. And then L times y times x, the expected value of that is L is a constant, so it's minus L times expected value of y times x tilde, which I've just left alone. And then I've got the expected value of x times minus ly tilde, and the transpose of all of that, so that comes out here, remembering that A, B transpose equals B transpose A transpose. And then finally the ly and the ly all transposed gives me this. It's expected value of L times y tilde transpose L transpose. The L's come out. It's L times expected value of y tilde transpose times L transpose. L comes out because it's a constant and expectation is linear, so the constant comes outside. And expected value of y tilde is sigma y there. Looking at what I'm left with, let's look at this one. Expected value of x tilde y tilde is we'd have to go back to here to realize that. So L k is equal to sigma x tilde y tilde minus times sigma y inverse, and I can and there's k's there, and I can solve for this. That's the expected value of x tilde y tilde. I can solve by multiplying both sides by sigma y inverse, sigma y. on the right. So I should have Lk sigma y equals sigma x y minus. So that's what we have here. L times sigma y is equal to the correlation, the expected value of x tilde y tilde transpose. And this here is the same. It's just all transposed, so you have to transpose everything to see that. What we end up with is that, and then I've got L sigma L transpose, I've got L sigma L transpose, and I've got L sigma L transpose. They have the same form, except I've got minus, minus, plus. So 2 negatives, 1 positive gives me overall 1 negative minus L sigma L transpose. So the covariance of the estimate is equal to the covariance of the prediction with a correction factor, this L sigma y L transpose correction factor. This has been an awful lot to take in. I don't really apologize for going so quickly because we're going to go over this several times, and hopefully each time we go over it you get a little bit more out of it. But I do want to pause briefly and try to summarize and bring all of these results together to give an idea of how it's going to be used. A lot of calculations, a lot of math. What do we care about here? Well, we care about all of it, but the output of this process has two parts. Part one is a state estimate. At the end of every iteration, after I make a measurement, I've computed the best guess that I could compute at this point in time of the present state value, and that's x hat k plus. Somewhere embedded in there is battery state of charge. Somewhere embedded in there is an estimate of the hysteresis state. Somewhere in there is a diffusion voltage estimate in that state vector. But that is my best estimate of the state vector at this point in time. We also have a covariance estimate for the state error. And that gives us uncertainty on my estimate. It gives me the ability to compute error bounds. And while this wasn't really something we set out to build into the algorithm, it turned out that the solution required that we compute these covariances, and because we have computed them, we can take advantage of them to compute the error bounds in our estimate that vary with time and give us an idea of, okay, the state of charge is 50%, but 50% plus or minus what? And if I take, say, for example, a Gaussian random variable is more than 99% likely to be within plus minus 3 sigma of its mean, I could find sigma by looking at the diagonal of the covariance matrix, finding the diagonal element corresponding to the state of charge state. That is the covariance of the state of charge state. Taking the square root, that's the standard deviation of the state of charge state. If I want plus or minus 3 sigma, I just multiply that by 3, and that gives me error bounds that I've got very high confidence that the true state is within the estimate x plus and plus minus 3 sigma. So very, very helpful. This is not showing up too well on the screen. I'm going to blow it up a little bit here. That didn't help a lot either. So hopefully your printout is better looking than this. But the generic Gaussian sequential probabilistic inference solution has two fundamental steps, and we're going to develop sub-steps because this is still not an algorithm. This is still math. I need to derive an algorithm, a sequence of computer steps that I can execute. But it says every time I make a measurement, I'm going to compute an estimate of the state. And that estimate is computed by having first computed a prediction of the state and a prediction of what I would measure, comparing that to what I did measure, computing this gain vector L, which is called the Kalman gain, by the way, and adding them together like that, and that is my state estimate. I also compute an uncertainty or a covariance of the state estimate, having already somehow computed a prediction covariance and modifying that by computing an output uncertainty covariance and pre and post multiplying by the common gain, just like that. We have all of the definitions summarized here. All of the definitions that are used in this derivation are summarized, and that is the generic probabilistic inference solution. This applies to a system that has linear dynamics. It applies to a system with nonlinear dynamics. This exact same set of math only assumes at this point that the noises are white, the noises are Gaussian, and in fact that the state is a Gaussian random vector. So if that's even close to true, I can apply the generic steps with additional assumptions on whether the system is linear. So if the system is linear, I can evaluate these equations to come up with the linear common filter. Or if the system is nonlinear and I make a couple of assumptions, I get the extended common filter. Or if it's nonlinear, I make different assumptions, I get the sigma point or unscented common filter. All of these are useful to think about for a battery management system. The linear common filter, not so much, but it's a stepping stone to get us to the other two, which can be quite useful in a battery management system. So, I can't look around the classroom. I can't look into your eyes and see if you're following or not. So I imagine there's some possibility that this is confusing. In the next step, though, what we're going to do is we're going to look at this solution. We'll assume the derivation. We'll look at this solution and break it up into smaller baby steps. And then those baby steps, there's going to be 6 of them. And we will then apply those 6 baby steps to derive the common filter, and we'll spend some time, a lot more time, with intuition there and understanding and examples of the linear common filter, and then proceed with the nonlinear derivations as well. So hang in. I think it's going to get better. I think we're through the worst of it, and we'll get these other derivations done quickly.